Late April, 1944. Yokosuka Naval Air Technical Arsenal, 30 miles south of Tokyo. Commander Minoru Genda stood before the aircraft that had just arrived under armed guard, his expression unreadable. The Grumman F6F-3 Hellcat bore scars from its forced landing in the waters off Truk Lagoon 3 weeks earlier. Salt corrosion marked the cowling. The fabric on the control surfaces showed water staining, but the fighter remained structurally intact, its massive Pratt & Whitney R2800 engine recoverable, its systems largely undamaged. What troubled Genda was not the aircraft's condition, it was what this fighter represented. For 18 months, Japanese naval aviators had been reporting encounters with this American carrier fighter. The reports were consistent and deeply concerning. The Hellcat was faster than the Zero. It was more heavily armed. It could absorb damage that would destroy any Japanese fighter. And now, for the first time, Japanese technical intelligence possessed an intact example to examine in detail. Genda had flown Zeros in combat over China. He had helped plan the attack on Pearl Harbor. He understood aircraft capabilities at the most fundamental level, but as he walked slowly around the Hellcat that morning, running his hand along the wing's leading edge, feeling the thickness of the aluminum skin, he recognized something that would reshape Japanese understanding of American fighter design. This was not merely a superior aircraft. This was evidence of an entirely different approach to fighter aviation, an approach that prioritized pilot survival as highly as combat performance. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The journey to this moment had begun 2 years earlier, on August 7, 1942, when American forces landed on Guadalcanal. That campaign would introduce Japanese pilots to a new generation of American fighters that would systematically dismantle every advantage the Zero had enjoyed during the war's first 8 months. The F-4F Wildcat, already in service, had proven that American fighters could compete with Japanese designs when flown with proper tactics. But the Hellcat would prove something far more threatening. It would demonstrate that American industry could produce fighters that were simply better in nearly every measurable category. The F6F Hellcat's development began in June 1941, 6 months before Pearl Harbor, when Grumman Aircraft Engineering Corporation received Bureau of Aeronautics approval to proceed with prototype construction. The Navy wanted a fighter superior to the F-4F Wildcat then entering service, with higher speed, better climb rate, longer range, and heavier armament. Most critically, the new fighter needed to operate effectively from aircraft carriers under the demanding conditions of Pacific naval warfare. Grumman's design team, led by Chief Engineer William Schwendler and Project Engineer Bob Hall, approached the challenge with methodical precision. They analyzed combat reports from European air warfare. They studied Japanese fighter capabilities based on intelligence assessments available in 1941. They calculated the performance requirements needed to achieve air superiority against the best enemy fighters. Their conclusion was straightforward. The new fighter would need substantially more power than any existing American naval fighter. The solution was the same engine that powered the Corsair, the Pratt & Whitney R2800 Double Wasp, an 18-cylinder 2-row radial producing 2,000 horsepower. This massive engine, weighing over 2,000 pounds, would give the Hellcat the power needed to carry heavy armament, substantial armor protection, self-sealing fuel tanks, and still achieve performance superior to enemy fighters. The design philosophy was revolutionary for carrier aviation. Rather than minimizing weight to maximize performance, Grumman engineers accepted substantial weight in exchange for comprehensive protection and overwhelming firepower. The XF6F-1 prototype first flew on June 26, 1942, from Grumman's facility in Bethpage, Long Island. Test pilot Robert Hall reported excellent handling characteristics and impressive performance, but even before the prototype flew, combat intelligence from the Pacific was changing requirements. Reports from Guadalcanal indicated that Japanese Zeros could outclimb American fighters at medium altitudes. The F6F needed better high-altitude performance. Grumman responded by switching to the more powerful R2-80010 engine with a two-stage supercharger, creating the F6F-3 variant. This modification increased high-altitude performance substantially, giving the Hellcat superior climb rate above 15,000 feet. The change delayed production by only weeks, a testament to Grumman's engineering efficiency and American industrial flexibility. The Navy accepted the delay as necessary to ensure the Hellcat could dominate Japanese fighters at all altitudes. Production F6F-3 Hellcats began reaching fleet squadrons in January 1943. The aircraft that would become the Navy's premier carrier fighter for the remainder of the war represented a complete package optimized for naval air combat. Empty weight of 9,238 pounds reflected substantial structure and protection systems. Maximum takeoff weight reached 15,413 pounds when fully loaded with fuel, ammunition, and external stores. The weight penalty compared to lighter Japanese fighters was deliberate and accepted as necessary for the comprehensive capabilities American doctrine demanded. The Hellcat's dimensions revealed a fighter designed for carrier operations. Wingspan of 42 feet 10 inches provided excellent low speed, handling for carrier approaches. Length of 33 feet 7 inches fit standard carrier elevator dimensions. Height of 13 feet 1 inch allowed clearance in carrier hangars. The wings folded upward hydraulically, reducing width to 16 feet 2 inches for efficient deck storage. Every dimension was calculated to maximize the number of fighters that could be operated from fleet carriers. But the Hellcat's true advantage lay in systems integration. 6 50-caliber Browning M2 machine guns, 3 in each wing, provided overwhelming firepower. Each gun was fed by a 400-round ammunition box, giving 2,400 rounds total capacity. The installation was designed for reliability under the violent maneuvering of air combat. Ammunition feed systems were tested extensively to prevent jams. Spent cartridge ejection was positioned to avoid damage to the aircraft structure. Gun charging systems allowed pilots to clear jams without leaving the cockpit. Protection systems represented American design philosophy at its most comprehensive. 212 pounds of armor plate protected the pilot from behind, below, and on both sides. The armor was face-hardened steel, positioned to stop 20mm cannon shells and rifle-caliber bullets from any angle except directly ahead. Bulletproof glass 40mm thick protected the pilot's head. The windscreen itself was laminated construction that could absorb battle damage without shattering. Even the instrument panel featured an armored plate to protect vital instruments from frontal attacks. The fuel system incorporated self-sealing tanks throughout, holding 250 gallons internally. The self-sealing technology used multiple layers of rubber compounds that swelled when exposed to fuel, automatically sealing bullet holes and preventing fuel loss. Additional protection came from carbon dioxide fire suppression systems that could flood the fuel tanks with inert gas if fire was detected. The comprehensive approach to fuel system protection reflected hard lessons learned from early war combat when unprotected fighters burned catastrophically from single hits. The cockpit layout prioritized pilot effectiveness under combat stress. Every control was positioned for intuitive operation. The throttle on the left side quadrant included integrated controls for propeller pitch, mixture, and supercharger stages. The control stick featured gun triggers and radio transmit button within easy reach. Rudder pedals incorporated adjustable footrests for pilot comfort during long missions. The instrument panel arranged gauges logically, with critical flight instruments directly in front of the pilot and engine instruments to the right. Visibility from the cockpit exceeded any previous American carrier fighter. The canopy was a frameless bubble design, offering near 360-degree vision with only minimal blind spots. Pilots could see directly behind through clear panels in the canopy's rear section. The view downward over the cowling was excellent, critical for carrier landings where precise altitude control was essential. The raised seating position gave pilots a commanding view in all directions, invaluable for spotting enemy aircraft and maintaining formation integrity. The Hellcat entered combat on August 31st, 1943, when fighters from USS Independence and USS Essex participated in strikes against Marcus Island. The debut was successful but limited in scope. The true test would come 2 months later during operations in the Central Pacific, as American forces began the island-hopping campaign that would carry them toward Japan. It was during these operations that Japanese pilots would first encounter the Hellcat in significant numbers and begin reporting its disturbing capabilities. Lieutenant Junior Grade Edward Butch O'Hare had become America's first naval ace in early 1942, flying F6F Wildcats. Wildcats. By late 1943, he commanded. O'Hare's experience with both fighters gave him unique perspective on the Hellcat's advantages. The Wildcat was a scrapper, he later wrote in his combat assessment. You had to work for every advantage. The Hellcat just dominates. You can dictate the terms of engagement, and the enemy can't do much about it. The first major test came during Operation Galvanic, the invasion of Tarawa in November 1943. Hellcat squadrons from multiple carriers provided air cover for the invasion force and struck Japanese airfields throughout the Marshall Islands. Japanese defenders launched counterattacks using Zero fighters and bomber formations. The engagements that followed established patterns that would define Hellcat combat performance for the remainder of the war. American pilots consistently achieved favorable kill ratios, typically destroying 3-5 Japanese aircraft for every Hellcat lost. What made these results remarkable was not just the kill ratio itself, but the consistency across different squadrons, different carriers, and different pilot experience levels. Whether flown by combat veterans or newly trained pilots fresh from training squadrons, the Hellcat consistently outperformed Japanese fighters. The aircraft's inherent advantages, its speed, climb rate, firepower, and protection, created conditions where even average pilots could achieve success against experienced Japanese aviators. Commander David McCampbell would become the Navy's leading ace flying Hellcats, eventually credited with 34 victories. His experience illustrated how the Hellcat's capabilities enabled aggressive tactics. McCampbell developed what he called the running gunfight, using the Hellcat's superior speed to chase down enemy formations, attack from advantageous positions, and disengage before enemy fighters could respond effectively. The tactics exploited every Hellcat advantage while avoiding situations where Japanese fighters' superior maneuverability could prove decisive. By early 1944, Japanese naval aviation was reporting disturbing loss rates in encounters with Hellcat squadrons. The pattern was consistent across all theaters. When Zeros engaged Hellcats, the Americans achieved favorable exchange ratios. When Japanese pilots attempted to use traditional dogfighting tactics, exploiting the Zero's superior turn rate, Hellcat pilots simply refused to engage in slow-speed maneuvering, instead using superior speed and climb rate to maintain tactical advantage. When Japanese pilots attempted to disengage, Hellcats pursued relentlessly, running down enemy fighters that could not match American speed. The psychological impact on Japanese pilots was profound and growing. Throughout 1942 and early 1943, Japanese naval aviators had maintained confidence despite increasing American strength. They flew aircraft they understood intimately. They employed tactics proven effective through years of combat in China and the Pacific. They believed superior skill could overcome material disadvantages. But the Hellcat challenged these assumptions at a fundamental level. This was not an aircraft that could be defeated through better tactics or superior pilot skill. This was a fighter that simply outperformed Japanese designs in nearly every category that mattered in combat. It was in this context that the intact F6F-3 arrived at Yokosuka in late April 1944. The fighter had been recovered from shallow water off Truk Lagoon, after its pilot, Ensign Robert Kanze from VF-9 aboard USS Essex, had been forced to ditch following combat damage to his oil system on February 17th during Operation Hailstone. Kansei had been rescued by submarine, but his Hellcat had sunk in water shallow enough that Japanese salvage crews could recover it. The fighter was transported to Truk, then shipped to Japan aboard a fast transport, arriving at Yokosuka under circumstances of extraordinary secrecy. The examination that would follow would last 6 weeks. Japanese aviation specialists would dismantle every system, measure every component, test every material, and document their findings in technical reports that would be discovered by American occupation forces 18 months later. What they would discover would fundamentally alter Japanese understanding of American fighter design philosophy and reveal the enormous gap that had opened between American and Japanese aviation capabilities. The initial examination began on April 28, 1944, in a secured hangar at Yokosuka Naval Air Technical Arsenal. A team of 15 engineers, technicians, and test pilots assembled around the Hellcat under the direction of Commander Genda and Lieutenant Commander Takeo Shibata, Yokosuka's chief aeronautical engineer. Their assignment was comprehensive: document every aspect of the aircraft's design, construction, and capabilities. Understand how American engineers had achieved the performance Japanese pilots reported. Determine if Japanese industry could replicate any advantageous features. The team began with systematic photography from every angle. Wide shots captured the aircraft's overall proportions. Detail photographs documented construction methods, component installations, and manufacturing techniques. Each photograph was numbered and cross-referenced with written documentation. The process consumed the first 3 days, producing over 400 photographs that would form the visual record of the examination. Dimensional measurement came next. Teams used precision measuring instruments to record every aspect of the Hellcat's structure. Wingspan of 42 feet 10 inches, length of 33 feet 7 inches, height of 13 feet 1 inch with the tail down as it would rest on a TAFE, carrier deck, wing area of 334 square feet. The measurements were recorded in both American units as marked on the aircraft and converted to metric standards for Japanese technical documents. What immediately struck the examination team was the Hellcat's substantial construction. The aircraft felt heavy, solid, built to absorb punishment. The skin thickness exceeded anything in comparable Japanese fighters. Where Zero fighters used aluminum alloy as thin as 0.8 millimeters in non-critical areas, the Hellcat's skin measured consistently between 1.5 and 2 millimeters throughout most of the fuselage and wings. This single difference represented a design philosophy fundamentally different from Japanese practice. Lieutenant Commander Shibata noted in his initial assessment, "The aircraft demonstrates American willingness to accept weight penalties in exchange for structural strength. Every component appears over-engineered by our standards. This is not inefficiency. This is deliberate design choice, prioritizing durability and battle damage tolerance over minimum weight." The wing structure revealed sophisticated engineering that Japanese designers recognized but could not easily replicate. The main spar was a massive forged aluminum component running the wing's length from root to tip. Japanese engineers measured its dimensions carefully. The depth at the wing root exceeded 300 millimeters. The thickness of the spar caps, the upper and lower flanges that carried primary bending loads, measured over 30 millimeters of high-strength aluminum alloy. Creating forgings of this size and quality required industrial capabilities that Japanese manufacturers increasingly lacked. The forging process demanded large hydraulic presses capable of generating thousands of tons of pressure, heat-treating facilities that could handle components of this size, and most critically, quality control systems, ensuring consistent metallurgical properties throughout the forging. Japanese industry could produce forgings of this size in 1941 and early 1942. By 1944, with strategic materials in short supply and skilled workers conscripted for military service, consistent quality had become nearly impossible. The wing ribs, the span-wise structural elements that maintained the wing's aerodynamic shape, demonstrated manufacturing precision that particularly impressed the examination team. Each rib was stamped from aluminum sheet using dies that produced virtually identical components. Tolerances were measured in hundredths of millimeters. The ribs fit together with precision that required minimal adjustment during assembly. Japanese aircraft production, even before the war, relied heavily on hand-fitting individual components. Shimming, filing, and adjustment were standard practice. The Hellcat's components simply fit together as designed, indicating manufacturing quality and control that Japanese factories could not match. Attention turned to the armament installation. The 6 Browning M250 caliber machine guns represented firepower exceeding any Japanese fighter in service. Each gun was belt-fed from a 400-round ammunition box positioned inboard of the gun itself. The installation was engineered for reliability under extreme conditions. Ammunition feed chutes were smooth, curved sections designed to prevent jams even during violent maneuvering when G-forces affected ammunition belts. Spent cartridge ejection chutes directed brass and links overboard through carefully positioned openings that prevented damage to the aircraft structure. Japanese technicians examined the Browning guns themselves with particular interest. These weapons represented decades of American ordnance development and manufacturing experience. The M2 machine gun was a mature design, perfected through continuous refinement since its introduction in 1921. 1944. American manufacturers produced these weapons by the hundreds of thousands with extraordinary consistency. Each gun was essentially identical to every other gun. Parts were interchangeable. Reliability was exceptional. The examination team test-fired one of the Hellcat's guns that had been cleaned and serviced. The weapon functioned flawlessly through 250 rounds of captured American .50 caliber ammunition. No jams, no failures, no malfunctions. The gun's rate of fire reached approximately 750 rounds per minute, slightly slower than the theoretical 800 rounds per minute, but consistent with field conditions. Japanese aviation machine guns rarely achieved such reliability. The Type 99 20mm cannon, standard armament in later Zero variants, was prone to jamming and required constant maintenance. The discovery of the Hellcat's armor protection shocked even experienced Japanese engineers who understood American. Emphasis on pilot protection. The armor plate behind the pilot's seat measured 8mm thick, face-hardened steel, capable of stopping 20mm cannon shells from directly behind. Additional armor plates protected the pilot from below, 3mm of steel positioned to stop ground fire during strafing runs. Side armor panels, 6mm thick, protected against deflection shots from beam attacks. The total weight of armor exceeded 200 pounds, more than the entire empty weight of some components in Japanese fighters. The armored glass behind the windscreen measured 40mm thick, layered construction using multiple sheets of glass with plastic interlayers. Japanese engineers tested samples of this glass armor by firing 7.7mm rifle rounds at it from 20 meters. The bullets penetrated partially, but did not pass through completely. The glass cracked but did not shatter, maintaining sufficient transparency for the pilot to see through it even after taking damage. This level of protection was simply absent from Japanese fighters, where weight considerations had forced elimination of nearly all armor by mid-war. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The self-sealing fuel tanks represented technology that Japanese engineers had attempted to develop but never successfully implemented in production aircraft. The Hellcat's tanks used multiple layers of rubber compounds, sandwiching the aluminum tank structure. When aviation fuel contacted these rubber layers through bullet holes, the compounds swelled, automatically sealing the puncture and preventing fuel loss. The system added substantial weight to each fuel tank, but dramatically improved survivability. Japanese technicians deliberately punctured sample sections of the self-sealing tank material recovered from the Hellcat. They observed how the rubber compounds reacted to fuel exposure, noting the speed of swelling and the effectiveness of the seal. Tests showed that holes up to 12 millimeters in diameter sealed within 30 seconds of fuel contact. Larger holes sealed partially, significantly reducing fuel loss even if complete sealing was not achieved. The technology was elegant, effective, and entirely dependent on rubber compounds and manufacturing processes that Japanese industry could not replicate with available materials in 1944. The Pratt & Whitney R2800 engine dominated the technical examination as the component that enabled everything else. This massive power plant, weighing 2,065 pounds without accessories, produced 2,000 horsepower at takeoff and maintained impressive power output at altitude through its two-stage supercharger system. Japanese engineers had encountered this engine before in captured Corsairs and other American aircraft, but the Hellcat example provided the most complete specimen available for detailed analysis. The engine was carefully removed from the airframe and transported to Yokosuka's engine testing facility. Despite saltwater immersion during the ditching, the engine remained largely intact. The team disassembled the power plant completely, documenting every component and every assembly technique. What they discovered confirmed what Japanese engineers already suspected. American aero engine manufacturing had achieved quality levels that Japanese industry could not match. The 18 cylinders were precision-machined components with tolerances measured in thousandths of inches. Surface finishes on cylinder walls showed mirror-like smoothness, achieved through honing processes that removed microscopic imperfections. The piston rings were perfectly circular, fitting cylinder bores with minimal clearance. This precision was essential for maintaining compression and preventing blow-by, the leakage of combustion gases past the pistons that reduced power output and increased oil consumption. Japanese engines, even new examples fresh from factories, typically showed greater manufacturing variations. Cylinder walls were rougher, piston rings fit less precisely, oil consumption was higher, power output was lower than theoretical ratings. These differences stemmed not from inferior design, but from manufacturing limitations. Japanese industry lacked the machine tools, the quality control systems, and increasingly by 1944, the skilled workers needed to achieve American manufacturing standards. The R2800's two-stage supercharger system particularly impressed the examination team. Superchargers compressed intake air before it entered the cylinders, allowing engines to maintain power at high altitudes, where thin air would otherwise cause significant power loss. Single-stage superchargers were common in Japanese engines. Two-stage systems, where one supercharger fed compressed air to a blowf, second supercharger for additional compression, were far more complex. The R2800's two-stage system used sophisticated internal passages, intercoolers to reduce compressed air temperature, and precisely fitted rotating components operating at extremely high speeds. Japanese attempts to develop comparable supercharger systems had largely failed. The Nakajima Homare engine, intended to power advanced fighters like the Ki-84 Hayate, incorporated a two-stage supercharger, but suffered chronic reliability problems. Manufacturing quality varied between engines. Some examples performed adequately, others failed catastrophically. The inconsistency made the Homare unreliable in service, forcing pilots to operate engines conservatively to prevent failures. The R2800 demonstrated that two-stage supercharging could work reliably when manufactured with sufficient precision and quality control. Examination of cockpit systems revealed the comprehensive approach American designers took to pilot effectiveness. The instrument panel featured 27 gauges and indicators, providing complete information about aircraft and engine status. Flight instruments were logically arranged directly in front of the pilot. Engine instruments clustered to the right side. Warning lights indicated system status. Every gauge was clearly labeled with markings visible under all lighting conditions. Japanese pilots transitioning from Zeros to examine the Hellcat cockpit noted the marked difference in information available. Zero cockpits were austere by comparison, providing essential flight and engine information but little else. The philosophy reflected different approaches to pilot workload. Japanese designers minimized cockpit complexity, expecting pilots to operate aircraft based on experience and feel. American designers provided comprehensive information, allowing pilots to monitor every system and make informed decisions based on accurate data. The radio equipment represented another area where American technological advantages were overwhelming. The Hellcat carried a complete radio communication system, including transmitter, receiver, and interphone. The SCR-522 radio provided 4-channel capability, allowing selection between different frequencies for different purposes. One channel for air-to-air communication between fighters, another for air-to-ship communication with carriers, additional channels for tactical coordination and emergency frequencies. Japanese fighters by 1944 often had no radios at all. Early War Zeros included basic radio equipment, but reliability problems and weight-saving measures led to removal from many aircraft. Even when radios were installed, performance was poor. Range was limited, reliability was questionable, frequency selection was cumbersome. The absence of effective radio communication severely limited Japanese tactical flexibility, preventing the kind of coordinated attacks that American fighters executed routinely. The hydraulic systems throughout the Hellcat demonstrated sophisticated integration of multiple functions. Hydraulic pressure operated the landing gear retraction and extension. The wing folding mechanism used hydraulics to raise and lower the wings for carrier storage. The tailhook used hydraulic damping to absorb shock during arrested landings. The cowl flaps that regulated engine cooling were hydraulically actuated. A single engine-driven hydraulic pump pressurized the entire system, with accumulators storing pressure for emergency operation if the pump failed. Japanese fighters relied primarily on manual or pneumatic systems. Landing gear in Zeros retracted and extended manually, requiring significant pilot effort and time. Wing folding, when present, was manual. The proliferation of hydraulic systems in the Hellcat reflected American industrial capacity to produce reliable hydraulic components and American willingness to accept additional weight and complexity in exchange for pilot workload reduction and improved reliability. After 6 weeks of examination, the Yokosuka team prepared comprehensive technical reports documenting their findings. These reports, written in precise technical language, detailed measurements, described systems, and offered assessments of American capabilities. The reports were classified secret and distributed to Japanese Navy headquarters, other technical facilities, and aircraft manufacturers. Copies would eventually be discovered by American occupation forces in September 1945 and translated, providing insight into what Japanese engineers understood about American fighter capabilities. The report's conclusions were sobering. In virtually every category examined, the Hellcat demonstrated superior design, superior materials, superior manufacturing quality, and superior systems integration compared to Japanese fighters. The gap was not small or easily closed. It represented years of industrial development, massive investments in research and tooling, sophisticated supply chains providing high-quality materials and components, and most critically, manufacturing quality control that Japanese industry could not match with resources available in 1944. Lieutenant Commander Shibata's summary assessment captured the examination's essential finding. The F6F represents a complete fighting system optimized for carrier operations and pilot survival. Every component serves multiple purposes. Every system integrates with others. The aircraft accepts substantial weight penalties to achieve comprehensive capabilities. Japanese industry cannot replicate this approach. We lack the manufacturing precision, the material quality, the component reliability, and the resources to produce comparable aircraft in meaningful numbers. The technological gap is substantial and widening. The examination's findings were shared with combat units through classified briefings and tactical combat bulletins. Pilots were informed of the Hellcat's capabilities based on physical evidence rather than combat reports alone. The bulletins were frank about Japanese disadvantages. The Hellcat was faster at all altitudes. It could outclimb Zeros above 15,000 feet. Its firepower was overwhelming, Its protection made it difficult to destroy even when hit repeatedly. Most critically, American pilots were trained to exploit every advantage, avoiding slow-speed combat where Japanese fighters retained maneuvering superiority. The tactical recommendations flowing from the examination were explicit. Avoid engaging Hellcats when possible. If engagement was unavoidable, attack only from advantageous positions, preferably from above and behind with altitude to trade for speed. Never attempt sustained combat. Strike once and disengage immediately. Never follow damaged Hellcats, as American fighters often feigned damage to lure pursuers into traps. These recommendations acknowledged what the examination had proven. Japanese fighters could not defeat Hellcats in sustained combat. Survival depended on avoiding engagement or striking from positions of overwhelming advantage and immediately withdrawing. The examination of the captured Hellcat occurred as Japan's strategic position deteriorated beyond recovery. In June 1944, just weeks after the Yokosuka analysis concluded, American forces invaded the Mariana Islands. The Japanese Navy committed its remaining carrier strength to stop the invasion in what became the Battle of the Philippine Sea. The engagement would prove the final, devastating demonstration of Hellcat superiority. On June 19, 1944, Japanese carriers launched over 300 aircraft against the American invasion fleet. Hellcat squadrons from 15 American carriers intercepted the attacking formations in what American pilots would call the Great Marianas Turkey Shoot. In 8 hours of combat, American fighters destroyed approximately 300 Japanese aircraft while losing only 29 of their own. The kill ratio of better than 10-1 reflected not just pilot skill, but the overwhelming technical advantages the Hellcat examination had documented. Japanese pilots who survived the battle reported experiences that confirmed everything the Yokosuka engineers had discovered. The Hellcats were everywhere, moving faster, climbing higher, shooting more accurately. Zero pilots attempting traditional dogfighting tactics found American fighters refusing to engage in turning combat, instead using speed and altitude advantages to attack repeatedly from positions of superiority. When Japanese pilots scored hits on Hellcats, the American fighters often continued fighting, their armor and rugged construction absorbing damage that would have destroyed Zeros. Commander Genda, who had examined the captured Hellcat at Yokosuka, understood immediately what the battle meant. Japanese naval aviation had been effectively destroyed. The experienced pilots who had begun the war were nearly all dead. Their replacements, trained in abbreviated programs with limited fuel and obsolescent aircraft, could not compete with well-trained American pilots flying superior fighters. The technical advantages the Hellcat represented had combined with overwhelming American numerical superiority to create conditions where Japanese victory was impossible. By late 1944, Hellcat production had reached extraordinary levels. Grumman's factories produced over 500 aircraft per month, more than Japan's entire fighter production across all manufacturers. American carriers operated Hellcat squadrons in overwhelming strength. Japanese pilots encountering American task forces faced dozens of Hellcats launched from multiple carriers, all coordinated through effective radio communications, all flown by adequately trained pilots in aircraft superior to anything Japan could produce. The examination at Yokosuka had revealed the technical gap. The Battle of the Philippine Sea demonstrated the operational consequences, but the story did not end there. In October 1944, during the Battle of Leyte Gulf, Hellcat squadrons participated in the destruction of the remaining Japanese carrier force. In February 1945, during strikes on Tokyo itself, Hellcats swept aside Japanese defenders and established air superiority over the home islands. In the Okinawa campaign from April through June 1945, Hellcats provided air cover that made Japanese air attacks suicidal endeavors. The kill ratio statistics told the story with mathematical precision. Hellcat pilots were officially credited with 5,156 aerial victories during World War II, destroying more enemy aircraft than any other Allied fighter type. Against these victories, only 270 Hellcats were lost to enemy aircraft in combat, The kill ratio of approximately 19-1 exceeded even the most optimistic projections from early 1944. These numbers reflected everything the Yokosuka examination had documented: superior speed allowing American pilots to dictate engagement terms, superior climb rate permitting attacks from altitude, superior firepower destroying targets with brief firing passes, superior protection allowing damaged Hellcats to return home. The aircraft's technical advantages, combined with adequate pilot training and overwhelming numbers, had created conditions where Japanese pilots faced impossible odds every time they encountered Hellcat formations. When American occupation forces arrived at Yokosuka Naval Air Technical Arsenal in September 1945, they found the examination reports filed carefully in technical archives. American intelligence officers translated the documents, discovering detailed Japanese assessments of the Hellcat's capabilities. The reports confirmed what American forces already knew, but provided insight into how thoroughly Japanese engineers had understood their disadvantages. The captured Hellcat itself had likely been scrapped or destroyed during the final months of the war, when American bombing intensified and Japanese forces prepared for invasion. No records indicate what happened to the specific aircraft examined at Yokosuka. It vanished into the chaos of Japan's defeat, its lessons learned but its physical form lost to history. The story of the captured Hellcat examination represents more than technical intelligence. It symbolizes the moment when Japanese aviation specialists confronted the full magnitude of American industrial and technological superiority. The engineers at Yokosuka understood aircraft design at the highest level. They recognized sophisticated engineering when they encountered it. They could calculate the resource disparities and manufacturing quality differences that made the Hellcat possible. But understanding the problem did not provide solutions. Japan lacked the industrial capacity, the material resources, the manufacturing precision, and, most critically, the time to close the gap. The Hellcat went on to serve beyond World War II, continuing in American naval service until 1954, when the last examples were retired. The fighter had achieved what its designers intended, a carrier-based fighter that could establish and maintain air superiority against any opponent. For Japan, the encounter with the Hellcat marked the end of any illusions about matching American capabilities. The examination at Yokosuka provided proof, written in aluminum alloys, armor plate, and manufacturing tolerances, of the vast gulf separating the two nations' industrial capabilities. Japanese pilots who survived the war never forgot the Hellcat. They spoke of it with respect bordering on awe, the American fighter that could not be defeated through skill or courage alone. The captured example examined at Yokosuka had told them why. Every system, every component, every design choice reflected a nation's industrial might applied without compromise to creating the best possible weapon. Against such capability, determination alone was insufficient. The Hellcat's legacy endures in the kill ratio statistics, in the examination reports discovered after the war, and in the memories of pilots who flew them or faced them. It remains the definitive example of how superior technology, adequate resources, and sound design philosophy combine to create decisive military advantage. For Japanese aviation, the Hellcat represented an opponent that could not be overcome, a standard that could not be matched, and ultimately, evidence of why the Pacific War's outcome was never truly in doubt once American industrial power reached full mobilization. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.